Hello, everyone. I'm Nawel Jmail, Doctor Engineer in Neurosciences from Sfax University, Tunisia, and Aix-Marseille University, France. I am really delighted to be here today as an invited speaker for the Magnetism and Magnetic Materials Summit. And I will try to talk today for a thematic about enhancing epilepsy diagnosis using MEG signals. So my presentation will follow these steps. I will talk for a general context. I will introduce epilepsy, magnetoencephalography, present epileptic network connectivity among MEG and intracerebral EEG, and I will finish with some conclusion and perspective. So as you may know, neurological disease occupy an important part of the world's disease burden. And epilepsy is considered as a second leading cause of hospitalization for neurological disease. And it affects around 50 million people around the world. We are dealing about 4 to 10% for 1,000 subjects. 20% of cases are misdiagnosed, either because the health personnel are not sufficient enough to be specialized, or because the diagnosis of this illness will wander at least on average 5 years. Also, we will talk about 80% of epileptic subjects that would be seizure-free if they had a good treatment. Also, we are living in a world in developing technology, which is really amazing. Hence, the trend today is about developing more decision support tools in order to improve diagnosis for chronic disease, and in particular, neurological one. Hence, we are talking about e-neurology, e-epilepsy. These supporting tools would be necessary to support neurologists in order to define epileptogenic zones, the region of excessive discharges, using modalities of cerebral registration. Here we are dealing about signal processing of electrophysiological signal, of anatomical images, integrating advanced technique, and providing e-epilepsy software to boost diagnosis and ensure more well-being of patients. So for the epilepsy, as you may know, there is about 30% of epileptic cases which are diagnosed as drug resistant, which means medicine wouldn't stop or control the seizure. This is, as Talrak and Bangkok said, that there is a minimum of amount of cortex that should be removed in order to render the patient seizure-free. To do so, we are analyzing and studying several recording techniques as the non-invasive and the invasive one. So electroencephalography and magnetoencephalography both are non-invasive technique. A sample placement, as you may see here, a simple helmet to register the cortical activity, and they present both a high temporal accuracy. Another reference method, which is too important also in the diagnosis of pharmacoresistant epilepsy, is the intracerebral EEG. Here we are implemented electrodes strictly in the brain in order to register and record the activity of neurons. But these techniques depend strictly of the result of the surface result in order to claim the explored region. So for the magnetoencephalography, which is a brain recording or cortical recording of magnetic activity, this technique could register electrical activity that originates from electroencephalography or from electrical activity of the neurons. MEG presents an important advantage over EEG. In fact, it is less or small effect of the head geometry, and especially the skull. And also it doesn't require a reference like EEG. So here we are talking of the use of MEG, which become more and more recommended and widely studied and analyzed in perceptual and cognitive brain process to localize regions that could be affected by the pathology before surgical removal, and to define the function of various parts of the cortical activity. And of course, it is also used in neurofeedback techniques. I have, in fact, elaborated this project in collaboration with several members and the team leader of the Institute of Neuroscience and System, Professor Christian Georges Bénard. Our laboratory, in fact, is installed in the Neurophysiology Department of Latin Hospital, Marseille, France. We have a magnetoencephalography system with 238 captors for the neuroimaging. Our lab is equipped with stimulation apparatus, including video projection and SPACS calibrated system for auditory system. You can visit our laboratory and our platform of Marseille MEG-EEG platform with this link. So analyzing MEG-EEG, so the magneto signal or the magnetic signals, it will depict several activity, transitory one and the spiky one or spikes and oscillatory activity. For a long time, spikes were used as the best biomarkers, in fact, to define epileptogenic zone and during the diagnosis of epilepsy. But the last 2 decades, the researchers and the neurologists are oriented much more for studying oscillatory activity from the low gamma to the highest gamma, HFO, the high frequency oscillation, as a second biomarker seen in MEG. The first question that arises in this situation is whether these activity, the oscillatory one and the transitory one, could involve the same brain network. Answering the question, it requires, of course, advanced pre-processing chain in order to compute epileptic MEG connectivity and confront them between 2 biomarkers, which is transitory and oscillatory, and between 2 modality of registration, which is MEG magnetoencephalography and intracerebral EEG. At the clinical level, this will boost the diagnosis of neurologists and will help them, especially during the pre-surgical assessment of epileptic patient and during the removal of the epileptic tissue or cortical tissue. In this project, we deal with the rich databases. We have 10 recordings of MEG signal, which are recorded on 2 systems, CTF1, which is located at La Salpêtrière Hospital, Paris, and the 4D, which is located at the Latiman Hospital, Marseille. We have also 10 recordings of this patient from the intracerebral EEG according to Taleyrac stereotactic method. And of course, we have simulated 1,000 iterations for each databases, which respect the same morphological frequency features as the actual studied signals. So the goals here of this project is, in fact, to emphasize the importance of MEG during the diagnosis of epilepsy. This is why we are wondering the results of the epileptic networks of MEG, and hence we propose to confront MEG, epileptic MEG connectivity networks versus intracerebral EEG. It is about a double comparison about 2 types of biomarkers, oscillation versus transitory activity, and 2 types of modalities, magnetic one, which is surfacing, versus electric one, which is invasive technique. So this is why we separate these activities, we compute their networks, and hence we define the epileptic networks among the both biomarkers. Here, I'll present to you our strategy. I'll try to make it short and sweet. We start first by the inspection of the studied signal, the magnetoencephalography signal, then the detection of the both biomarker, the oscillatory one versus the spiky one. Then we proceed as our nullopathises that these biomarkers should be non-contaminated, should be pure, because we assume that they have different generators and they have different sensors, different sources, in fact, in the brain. That's why we propose two advanced techniques. Then we compute their network using the localization, the source localization techniques. So our first strategy here, in order to separate these biomarkers and to obtain non-contaminated activities and pure one, we studied in Jumaile of 2011 and 22 the stationary wavelet transform. We have decomposed the signal into coefficient. Then we project them on two types of masks, a pyramidal one for the transitory activity and a rectangular one for the oscillation. We used also the matching pursuit, which is the dictionary of Gabor atoms, and we detected the atoms that represent these biomarkers in a proper way. Our second strategy in the separation between these biomarkers is we did call phases. In these phases, we have only spikes. Then we project our signal on these phases to extract the transitory activity, and the oscillatory one would be the remaining activity. Hence, in these steps, we are dealing with detecting and recognizing pure non-contaminated biomarkers. So you may see here, these are the pyramidal shape of transitory activity. The blob one represents the oscillatory activity. And with this spikifying, we were able to detect only oscillatory activity as a second biomarker used among MEG. The second trouble in this project is about computing the network activity among MEG using the source localization. It's about going from the sensor level to mapping our brain. And this is after resolving the forward and the reverse problem in order to define for what extent can these techniques regain the activity measured from intracerebral EEG. So for the forward problem, we used, in fact, BrainVisa for segmentation, meshing cortex, and scalp surface. Then we made a registration between MRI and sensor using Brainstorm Toolbox. And finally, we fit sphere for each sensor tangent to the brain. For the inverse problem, in fact, we combine here our contribution also, that we propose to combine, in fact, two techniques for the resolution of inverse problem, which are MNE, minimum non-estimation, and bipolar technique, in order, in fact, to detect the ROE, which is the region of interest. As you may see in this short film, which is a window of 300 milliseconds, there is a local peak which represents of interest. It should be the region that should be studied and used in order to compute the network. As you may see here in the slide 19, we present the region of interest and the link between them and the strength of link. We have proved an important similarity rate between these epileptic networks, either for oscillatory activity or for transitory one among MEG and intracerebral EEG. It's about 57% for MEG and 100% for EEG. There's also a high concordance between networks leaders, which is 100% for intracerebral EEG and only 66% in MEG. The oscillatory network are much more complex in MEG, and the transitory one are much more extensive in intracerebral EEG. In fact, epileptic MEG connectivity networks did involve regions which not explored in EEG, and hence we can say that MEG connectivity networks could be supportive for an efficient pre-surgical mapping. So for the conclusion, fortunately, we made several results, important results. We proved and we made several guidelines in the separation between biomarkers, transitory and oscillatory one, detected and seen in magnetoencephalography. We studied their effect and we confront them with different other modality like intracerebral EEG. We proved the high concordance between MEG and EEG1 with more specific information in the epileptic generator spatial expand. And MEG network were able, in fact, to detect two important things, which are the seizure onset zone and the irritative zones as primary and secondary one. So likely, intellectual MEG transitory activity and oscillatory one are really complementary for a good planet pre-surgical mapping and during surgical intervention. Also, MEG could be seen as a practical tool in epilepsy decision-making process and during surgical intervention in order to make seizure-free. For the discussion and perspective section, the oscillation and transitory studied from MEG or obtained among MEG should be used for a good planning and a precise planning exploration for intracerebral EEG recording. We suggest to study both MEG biomarker, oscillation and transitory one, and this will lead to a further accurate information about seizure buildup, about the definition of the epileptogenic zone and the irritative zone. We suggest also to combine magnetoencephalography and electroencephalography registration to ameliorate the definition of epileptogenic zone, the region or the cortical region responsible of excessive discharges and responsible of seizure, in order to enhance epilepsy diagnosis and ensure more well-being of epileptic subjects. So here the used software in this project, and we are thankful for all our collaborators, either in Aix-Marseille University, the Institute of Neuroscience and System, the Department of Neurological of Latimer Hospital and La Salpatier Hospital, and also all the collaborators from Sfax University, here the funding of this project. Thank you very much for your attention. I am ready for the question session. Thank you.